Hi, my name is Scott Simpson, and today we'll be talking about orthogonality. So orthogonality is a property of many functions that you utilize in quantum mechanics that makes your life way easier. So we're going to talk about that. Orthogonality. And if we'll talk about what orthogonality is if you have two functions. So if you have two functions. We got psi sub I and psi sub j. If they are orthogonal, then we have two possibilities. We have where I does not equal j, and we have where I does equal j. So I and j are the same, meaning in the bottom case they're the same two functions, and the top case they're differing functions. Okay, so now, if we look at the probability density of them, basically multiplying the two together, get psi I, complex conjugate, psi j, tau, whatever we're integrating across. If we do this and the functions are orthogonal to one another, meaning, if they're orthogonal to one another and I is not equal to j, in this case, that'll result in a 0 for a value. If they are equal to one another and they are orthogonal to one another, if we do that same function, we will get 1 out. A lot of times we represent this function, you'll see it more so in physics than in chemistry, with a delta. This stands for a Kronecker delta function, and you'll see this a lot. But luckily, this property makes many derivations way easier, especially when you get to later on in quantum mechanics. So, let's look at an example of this. We're going to consider a function. We're going to look at when we have the same function and when we have differing functions. So, example. Consider a system with the normalized wave function of psi n. So we're going to indicate our function has a subscript n. It's a function of x is equal to square root of 2 sine n pi x. So in this case, this function's been normalized, meaning this is our normalization constant. If we integrate across the region that this is normalized, if we do psi times psi, we should get 1. Okay, where n is the energy level, and must be a positive whole number. Show that psi n of x, so with a subscript n, and psi m with a subscript m, meaning it's the same thing, but we've just changed the value of that n there, are orthogonal. In the region of 0 to 1. So those are the integration limits that we have. And now we're trying to show, in terms of this function, that it's orthogonal. Meaning, when we have the same function, we should get a 1 out, but when we have differing functions, we should get a 0 out. So, let's look at that. Let's start by first looking at where the functions are different. We know what answer we should get, so that should be relatively easy. Psi star n of x, complex conjugate of that, then we have m of x dx. So let's plug in some values here. When we do that, we get integral square root, we go from 0 to 1, square root of 2 sine n pi x times square root of 2 sine m pi x dx. And if you notice, we didn't do anything with our complex conjugate because we have no i's in there, so we didn't have to worry about it. Let's pull out the square roots of 2 multiply to one another, so we get 2 out front, integral sine n pi x times sine m pi x dx. Now, there's a couple different ways you could do this. You could switch these to cosines with another function. I prefer just to evaluate this integral as it is, but it really depends on you. So what we're going to do, or what I would do, is look up a generic integral that looks something like this in a reference table, and I in fact did find one. So from reference table, we get the integral sine ax times sine bx dx. If you evaluate that, you get sine a minus b x all over 2a minus b plus sine a plus b x to a plus b. Okay, so we're going to utilize that to solve this integral right here. Once we do that, then we should be on our way to getting to the solution. Okay, so let's plug this in. We still have that 2 out front. In this case, our A, we're going to set our A equal to n pi, our B equal to m pi. So let's do that. Let's start plugging some stuff in. We get sine n pi minus m pi x all over 2 minus n pi, or n pi minus m pi. Okay, plus sine n pi plus m pi x all over 2 times n pi plus m pi. And we got to go from 0 to 1. Let's evaluate. Let's simplify this a little bit further. We can pull out some pi's and make this look a little bit nicer. That's what I prefer to do. So we're doing it. Okay. We get sine. We got n minus m pi x 2 times pi n minus m plus sine n plus m pi x divided by 2 pi n plus m. And again, we still got to evaluate from 0 to 1. Okay. So now, when we do that, let's evaluate. We get 2 sine n minus m times pi 2 pi n minus m. In this case, x is equal to 1. We'll do the other x is equal to 1. Sine n plus m pi all divided by 2 pi n plus m. Now, the 0 terms, if we take basically this whole term up top, this is going to become sine of 0, which of course is 0. So that first term becomes 0, and the second term, the exact same thing happens. So those drop out. Okay. Now, what we get to as our overall result is 2 times sine n minus m pi over 2 pi n minus m plus sine n plus m pi over 2 pi n plus m. Okay, this looks complicated, but you can do a couple of tests. You can plug in different values of m and n, and remember they have to be whole number values, so if they're anything different, like decimals, that's not going to work. We specified at the beginning whole number values. If you plug in any whole number values that are not equal to one another here, what you always result in is some factor of pi, and that will be 0 for the sine function. So in fact, this ends up being 0. Okay, so we showed when the two functions are different, but what about when the two functions are the same? To prove that it's orthogonal, when they're different, they have to be equal to 0. When they're the same, they have to be equal to 1. So let's start with where they're the same function. And when we do that, we hopefully get to a point where it's equal to 1. Okay. So if n is equal to m, then we get the following. Start off with our simple integral, n x complex conjugate of that function dx. We can plug in for this integral square root of 2 times sine n pi x times square root of 2 sine n pi x dx. Okay. Combine like terms together. What we end up getting is 2 times, oh, we forgot our integration limits. Our integration limits are again going from 0 to 1. So we get sine squared n pi x dx. And again, this is a complicated integral. What you can do is you can look up this up in a table of integrals. So from table of integrals, you can look it up, but you get sine squared of dx is equal to x over 2 minus 1 over 4b sine of 2bx. In this case, our b is going to be equal to n pi. So we can use this to solve this integral. We get 2 times x over 2 minus 1 times 4 times b. In this case, our b is n pi, sine of 2 n pi. Evaluated from 0 to 1. Okay. If we do that, let's see what we get. We get 2 times 1/2 x minus 1 over 4 n pi sine of 2 n pi. Oh, we've got an x in here. N pi minus We got 0 over a half, so that's 0, plus, again, we're going to have sine of 0 in here. That's another 0. Okay. This term here, the second one, it looks like it depends on whatever the value of n is then, for whatever you get. But again, any whole number integer of n, or any whole number integer, whole number that you put in for n, you're still going to result in a sine function that results in a 0 value. So this term actually here becomes 0. So what we're left over with is 2 times 1/2, which is, of course, 1. So we've shown when a function is normalized and if it's orthogonal, if they're differing functions, the result will be 0. If they're the same function, the result will just be 1. Now keep in mind, if you notice, there hasn't been an operator in between these two functions. That can change this quite a bit, so keep that in mind. So with that, I'd like to thank you, and if there are any questions, please leave a comment below or feel free to send me an email. Thank you.